Hello, everybody. So we are ready to start chapter 3 in Calculus 3, which is Math 213. Chapter 3 is on vector-valued functions. So now you know all about vectors, having studied chapter 2. And now we go into calculus, the calculus of functions whose range is a set of vectors like R2 and R3. Okay, so this is a sort of a brand new type of functions, although you have studied parametric functions, which are quite similar. But we now get to do calculus, which means we are going to do derivatives and integrals, but mostly derivatives, and other things like limits and study continuity. All right, so let's get to it. Chapter 3 is kind of short. It only has 4 sections. And even the last part of section 4, we will not be studying much in detail, okay? So it'll be a quick chapter, but let's get started on vector-valued functions. I'll be sharing the screen now. All right, so section 3.1 on vector-valued functions. You could also write, what are these vector-valued functions? You can think of these functions, which I'll be talking about more precisely in just a minute, not spaces, space curves. Okay, now the space could be in plane. All right, so in calculus 1 and 2, and before that, like in pre-calculus, you remember, basically we were just talking about these functions on the reals, and these are the real valued functions on the reals. So that means you have x that gets sent to y. And so the entire graph can be seen this way. For each x, there's a y involved. And if the function is continuous, you will see a continuous curve like this, or maybe a straight line. It could have a sharp point, which would make this not differentiable. But the whole idea of any function is that you enter something, okay, called x, an input value, and then some specific and unique y value comes out, which we will call y or f of x. All right, so now in this chapter we begin. Actually, we may have talked about this in the past. You may have seen some of these in pre-calculus or trigonometry, or even in calculus 2. We'll be talking about the types of functions that would take the set of real numbers or a real number into a point in a 2 space or point in a 3 space. Right? So the function is going to be of this form, f of t. Now t is this element of the real numbers, and the result will be a vector determined by that value of t. So if it's on the plane, this will be a 2-dimensional vector valued function. You'll have xt and yt, where x and y are determined by that parameter t. If the codomain is the 3-dimensional space, it'll be xt, yt, and zt, where each coordinate is determined by the value of t, right? So this is very much like parametric functions. And in fact, you can think of these as parametric functions for now, and everything will be fine. Oh, by the way, sometimes people write this as xt of I and yt of j, plus, and then zt of k, of course. I don't particularly like this. I think the brackets, for me, a visual learner, it'll be much easier for me to see the brackets, but people are different. So maybe the other one would look better. All right, so here's an example. Let's say r of t. This is probably a very simple example. Cosine of t and sine of t. All right, now think of what are you thinking about right now? If I say x is cosine of t and y is sine of t, and as t goes from, let's say, from 0 to 2 pi. Now, you don't have to restrict the domain this way. T can go from negative infinity to positive infinity. In this particular function, it doesn't really matter if t goes to positive infinity or stops at 2 pi, because the graph, which I'm about to draw, is going to be the same. right? So maybe you can pause this and then try to figure out what the graph looks like. It has two components, so this would be a two-dimensional vector valued function. Okay, so did you think in terms of a circle? It is, right? And so the idea is this, okay? You notice here, x is cosine of t and y is sine of t, and cosine and sine often come in pairs, especially for our problems. And of course, what you want to do is making sure or understand how x and y are related to each other. In this case, x squared plus y squared, sometimes called the mother of all identities. I like that term. Cosine squared plus sine squared, and that's one, and it will stay one forever. If you're lying in your deathbed, cosine squared plus y squared will still be equal to 1. All right, so you know that this whole point, every single point, regardless of what t is, will be on the unit circle, and the unit circle being the circle of radius 1 centered at the origin, all right? And so here, when t is equal to 0, you have basically 1, 0, which is this point. When t is equal to pi over 2, you are at the point 0, 1, and in between it moves in the counterclockwise direction, right? And so when, let's see, t is equal to pi here, and when t is equal to pi or 3 pi over 2, and then this is where you end up with where t is equal to 2 pi, and within this domain, you make a complete cycle, and this is what the graph looks like. Okay. Now the graph itself, if you just, if you didn't have any of these things, the graph itself is only describing the range, right? Because it doesn't tell you what t corresponds to what value, what point. So, and the fact that it's counterclockwise is because it's cosine and sine. Now you can change this a little bit. If you have, for instance, r is equal to 10 cosine t, 10 sine t. Then what happens? Okay, this would be a big circle, right? It still goes, the movement is, or motion is still counterclockwise, but the radius is going to be 10. Try this. What happens if it's cosine of 10t, sine of 10t? Is this a big circle? No, this is still a unit circle. Because remember, if you see over here, the x squared plus y squared would be 100 cosine squared plus 100 sine squared. This will be 100. So the radius is the square root of that, which is 10. But for this one, x squared plus y squared is still 1. So it is a unit circle, radius 1. And what's the difference between this first example and the third example? Okay, this is going to be 10 times as fast. So if t stands for, time, which is really the reference to what the letter t is, if t represents, the time in seconds, so within the first 10 seconds, this will go from 0 to 20 pi, which means it goes around the circle 10 times. So 10 times as fast as R1. But the graph itself will look exactly the same, okay? Now let's try something else here. And just so you know, if this is 3 sine of t, 4 cosine of t. You know what? Let's go ahead and write this over here. This will be another example. Then what happens? Okay. Now you can try to plot points, but as much as plotting points is a good idea, it does take some time. Think in terms of how you can combine sine square with cosine square. I hope you can realize, or you can see, that x divided by 3 is sine square. So if you, sine of t. So if you square that, it's basically sine square of t. And then if you divide y, which is cosine of t, divide this by 4, that's cosine of t, and square that. So this is equal to 1, right? And now you can tell what kind of a object this is. It is a conic section, and it is it is an. All right, so you can tell this is got the semi-minor axis as length 3, and semi-major axis is length semi-major axis is of length 4, and it is an ellipse going this way. When t is equal to 0, oh, is that right? When t is equal to 0, oh, yeah. Oh, yeah, wait. Forget that. All right. So let's think about this. I switched sine and cosine as well, right? So this time, if t is equal to 0, what do you get? T is equal to 0, that means the sine is 0, this is 0, and this will be 4, right? So it starts right here. T is equal to 0 here. And what happens when t is pi over 2? That would be 3 here and 0 here, right? 3, 0, that's over here. So guess what? By switching the sine and cosine, you actually are now switching or uh, changing the orientation. This is going clockwise because the sine and cosine now switched. All right, so be careful, just because you have the cosine and sine doesn't mean that it's always round. Sometimes it could be something else. I'm going to give you one more thing here. What do you get this time if you have 4 cosine of t, 4 cosine of t? Think about that and let me know what you think. Okay, I hope this wasn't too confusing. You try to figure out how x and y are related to each other. Well, it's the same thing. So here, it's simply y is equal to x, which, by the way, is a straight line, right? Or radius, not radius. Lines don't have radius, radii. It's a straight line with slope 1 and intercept 0. So it is this line here, except it doesn't go any more than, this is supposed to be a 4. Because both x and y are the same value, and because cosine is multiplied by 4, it's not going to go more than 4, and it doesn't go down below -4, right? So here's the answer to this question. It basically goes back and forth between this point 4, 4, and -4, -4. Okay, so when t is equal to 0, for instance, you have 4, 4, and then when t is equal to pi over 2, then that's 0, 0. And then it keeps going this way until it stops here and then starts to go back and so on. Okay. And so again, be careful, just because you have cosine or sine, it doesn't mean that it's always going to be circular. All right, one more, this time for the first example in 3-dimensional case here. I'm going to give you this. Now, this will be one of our standard objects, so we'll be thinking about this quite a bit. All right, now remember, this is x, this is y, this is z. You'll have lots of questions on your homework where you'll be given the function and its graph, and you'll have a whole bunch of functions and a whole bunch of graphs, and you're trying to match them. And so those are great problems, by the way. You should pay very close attention and make sure you understand them. But let's see, this is R6, this goes from R, this is where T is, to R3, because now this is 3-dimensional, the codomain is 3-dimensional. But remember, for each T, each real value T, you have one point, and that point is a point in R3, and we are representing that point as the tip or the end or the terminal point of a vector, right? That's why it's called a vector valued function. Although technically, for parametric functions, the range is only the subsets of points, and we don't normally think of the results as vectors. So figure out what this is, and maybe you can draw a picture. Okay. Okay, so you notice here, x squared plus y squared is still equal to 1. And this is, since it's in 3-dimensional space, it's a vertical cylinder, all right? And I've drawn the vertical cylinder right here. And so what this is saying is, by the way, the vertical cylinder is not the answer, okay? Because t is just 1-dimensional. The domain is just 1-dimensional. So the range is going to be consisting of just single points. You will never have a surface that way. So what is that? Well, what this is saying is that regardless of what t is, the answer, cosine t, sine t, will be on this cylinder. It's going to be some point on the cylinder. And so hopefully you have figured this out. When t is equal to 0, you have the point 1, 0, 0. And that's this point, okay? Right. This is where t is equal to 1, x is 1, y and z are 0. And as it goes around, as t increases, of course, this kind of goes around this way. But notice here, z increases because z is equal to t. And so the idea is it'll start going this way and then turn around and then goes that way. Okay, so rather than, so basically what this is happening is this. It's a kind of a spiral. I can't draw this very nicely, but it's a spiral. And if it's an upward spiral, we have a special word for that in mathematics. This is called an helix. Okay, and later on we will study sort of a surface version of this, where the radius also changes with respect to another variable or parameter u, and then you have something that looks like an infinite helix, which is like a circular type of a parking lot, which sometimes I use for my background, virtual background on Zoom. But anyway, the spiral curve is called a helix, and we will be using this quite a bit, by the way. Okay, and I also did not mention here. A lot of times I don't mention this. What do I not mention? Well, a lot of times I don't mention what the domain is. What value can t be? And the natural understanding, or the obvious understanding, convention is that t can be anything you want, any real number from negative infinity to positive infinity. So this is sort of implied or understood, okay? And this is called the natural domain. And I'll come back to the idea of a domain in just a minute, okay? Now we'll be studying all sorts of different curves, and I'll show you more examples a little bit later. Okay, so hopefully this will help you understand what vector valued functions are. I still haven't talked about derivatives or integrals. You're right. Okay, so let's do that in the second portion. Part 2 of the video will start with limits. Can't wait, right? All right.